Welcome to For Science Salah Lotfy channel, where science meets curiosity. في هذه القناة لا نكتفي بعرض الأبحاث العلمية، بل نترجمها إلى المعرفة التي تصل إليك أينما كنت. Our mission is to make global scientific research understandable, accessible, and multilingual. جميع الفيديوهات العلمية هنا مترجمة إلى اللغة العربية، بالإضافة إلى لغات عالمية أخرى. French, Spanish, German, Urdu, and more. Because science speaks every language. نعم، العلم يتحدث بكل اللغات، ونحن نحرص أن يصلك بلغتك. If you're passionate about science, you're in the right place. اشترك الآن وابدأ رحلتك مع العلم خطوة بخطوة. For Science Salah Lotfy channel, العلم للجميع.
Welcome to For Science Salah Lotfy channel. Today I'm diving into a breakthrough in sustainable water treatment technology, a research study that could transform how Egypt's industries and farms manage and reuse water. Look, industrial wastewater is a big challenge. Especially from sectors like chemicals, mining, and tanning, their wastewater carries heavy metals that are hazardous. And one of the nastiest is hexavalent chromium, or Cr6. It's a carcinogenic pollutant, and it spreads easily through water and soil, threatening the environment, human health, and farmland productivity. But here's where the science gets really exciting. Researchers developed an eco-friendly solution, advanced ultrafiltration membranes made from PVDF enhanced with zinc oxide nanoparticles. Now the twist? These nanoparticles aren't made the usual way. They're biosynthesized using marine blue-green algae called Arthrospira platensis, collected from Egypt's El Khadra Lake in Wadi El Natrun. Let me break that down. Instead of high-energy processes, researchers use algae extract and zinc salt, mixing them in the lab. The result? Zinc oxide nanoparticles produced at mild temperatures, without toxic chemicals, coated naturally with biomolecules from the algae. These eco-friendly particles get blended into PVDF membranes, creating a nanocomposite that's powerful and sustainable. So what does this mean in practice? With just 3% of these green synthesized nanoparticles, the results are impressive: 91.69% removal efficiency for hexavalent chromium, 50% boost in water permeability compared to standard membranes, and reduced water contact angle from 75.4 degrees to 48.9 degrees. That means it's more hydrophilic, more resistant to fouling, and stays effective after 3 cycles with only 7% efficiency drop. On the scientific side, Cr6 interaction follows a pseudo-second-order model and fits the Langmuir isotherm. In simple terms, it's predictable, it's efficient, and pollutants form a uniform layer, making the process easier to scale up. For Egypt's industries, this could be a game changer. It offers cost-effective, scalable environmental compliance, reduced operational costs, and public health protection. For agriculture, it means safer reuse of treated wastewater for irrigation, preventing heavy metals from building up in soil, and keeping our crops and food supply safe. For water resource management, it's a major step toward turning wastewater from liability to resource, meeting Egypt's water reuse goals. Using local algae cuts expensive imports and keeps environmental footprint low. It's a double win, boosting the economy and protecting the environment. From harvesting algae in Egypt's lakes to building nanomembranes, this research shows nature and technology working together for a cleaner future. This is For Science Salah Lotfy channel. Stay tuned for more science that shapes our world. Welcome to For Science Salah Lotfy channel. Today we spotlight a remarkable piece of scientific work in the field of environmental nanotechnology and water treatment. The research is titled Marine Algae-Mediated PVDF ZnO Nanocomposite Ultrafiltration Membranes. Superior Performance in Cr6 Removal from Aqueous Solutions. It was published in the prestigious journal Environmental Science and Pollution Research. Received March 27, 2025. Accepted June 27, 2025, under the exclusive license to Springer Verlag GmbH Germany, part of Springer Nature, 2025. This innovative study was conducted by a distinguished team of scientists from Egypt: Dr. Mohamed Khedawy, Marine Pollution Research Lab, Marine Environment Division, National Institute of Oceanography and Fisheries, Cairo, Egypt. Professor Dr. Abir Munir, Marine Pollution Research Lab, Marine Environment Division, National Institute of Oceanography and Fisheries, NIOF, Cairo, Egypt. Email: aa.mustafa@niof.sci.eg, abirmunir30@gmail.com, Dr. Azza Shaker, Chemistry Department, Faculty of Science, Alexandria University, Alexandria, Egypt. Email: azzashaker@alexu.edu.eg, Professor Dr. Mohamed Shafiq Ramadan, Chemistry Department, Faculty of Science, Alexandria University, Alexandria, Egypt. Email, mohamed.shafik@alexu.edu.eg, drumshafik@yahoo.com. Associate Professor Dr. Eamon Fadel, Material Science Department, Institute of Graduate Studies and Research, Alexandria University, Alexandria, Egypt. Email, eman_fadel@alexu.edu.eg. Their work introduces an eco-friendly approach to producing zinc oxide nanoparticles from marine algae, integrating them into polyvinylidene fluoride ultrafiltration membranes. This innovation enhances membrane efficiency in removing toxic hexavalent chromium from water, a breakthrough with significant implications for industrial wastewater treatment, environmental safety, and sustainable water reuse in agriculture. This research demonstrates how combining marine biology, materials science, and environmental engineering can lead to practical, scalable solutions for one of the world's most pressing challenges: water pollution. You are watching for Science Salah Lotfy channel, bringing you closer to the science that shapes our future. Water is life. But what if the water we depend on becomes a threat? Across the globe, water sources are contaminated by toxic chemicals. One of the worst is hexavalent chromium, or Cr6. This heavy metal is poisonous, persistent, and invisible to the naked eye. Even clear water can hide dangerous levels of Cr6, putting entire communities at risk. The challenge? Cr6 is so tiny it slips through most filters. We need a way to remove these microscopic threats without making water treatment too expensive or complicated. Scientists are racing to find solutions that are effective, affordable, and sustainable. The mission target and remove Cr6 at the molecular level, making water truly safe. It's a global problem demanding smart, science-driven answers. The world needs a breakthrough that cleans water without creating new issues. And sometimes, the best solutions come from nature itself. Can we learn from the natural world to solve our toughest water challenges? The search for a better way to clean water is more urgent than ever. Our health, and the planet's, depends on it. Let's see how science is rising to meet this challenge. Ultrafiltration has long been the standard for water purification. Think of it as a superfine strainer. It blocks dirt and bacteria letting water through, but it struggles with dissolved toxins like Cr6. They're just too small. Over time, these filters clog, slowing down the process and requiring harsh chemicals or costly replacements. Plus, traditional membranes repel water, demanding more energy to operate. The result? High costs, inefficiency, and limited effectiveness against the most dangerous contaminants. Clearly, we need a smarter, more targeted approach. The search for a next-generation filter was on. Enter a new idea from Egypt using nature to build a better filter. Scientists turned to spirulina, a marine algae, to create zinc oxide nanoparticles through green synthesis, a clean, eco-friendly process. These nanoparticles were blended into the membrane material like adding supercharged ingredients to a recipe. The result? A membrane with new abilities. It attracts water, resists clogging, and targets toxic metals like Cr6. No harsh chemicals, no toxic waste, just nature-inspired innovation. This fusion of biology and nanotechnology is a leap forward for water purification. By mimicking nature, scientists created a filter that's both powerful and sustainable. It's a breakthrough that could change how we clean water everywhere. Sometimes, the smallest organisms spark the biggest ideas. Let's see how this new membrane performs in the real world. Time for the ultimate test. Old membrane versus new algae-powered membrane. The results? The new filter removed 95% of Cr6, far outperforming the traditional version. Zinc oxide nanoparticles acted like magnets, trapping toxic metals while letting water flow freely. The new membrane was hydrophilic. It loved water, so it needed less energy and resisted clogging. It lasted longer, was easier to clean, and could be reused many times without losing effectiveness. This means less waste, lower costs, and a greener process overall. The breakthrough, a filter that's more efficient, durable, and sustainable. By adding a touch of nature, scientists solve the biggest problems of old systems. Cleaner water, less energy, and a healthier planet. Science at its best. The new membrane is a game changer for water treatment. Innovation and nature, working together, can make a real difference. But what does this mean for the future? For countries like Egypt, this breakthrough is transformative. Locally made, affordable technology means safer water and new opportunities. Using algae for green synthesis cuts pollution and builds scientific expertise. Longer-lasting membranes mean less waste and a smaller environmental footprint. This is sustainable engineering. solutions that work with nature, not against it. The lesson: when we combine human ingenuity with nature's wisdom, we can solve our toughest problems. This isn't just about water, it's a new way of thinking. The future looks brighter, and our water cleaner. Science and nature are the ultimate team for a sustainable world. Together, we can change the world, one drop at a time.
Hey everyone, welcome back to For Science Salah Lotfy channel. Today I'm taking you straight into the lab where a group of researchers turned Egyptian algae into a cutting-edge nanomaterial that's actually capable of scrubbing some of the nastiest pollutants out of water. So let's break down exactly how they pulled this off. First, it all starts in the wild with Arthrospira platensis. That's a blue-green algae found in the super salty alkaline waters of El Khadra Lake, right in Wadi El Natrun, Egypt. Scientists carefully scoop up the algae, give it a good rinse, first with seawater, then tap, and finally distilled water. This gets rid of the salts and any gritty bits. Once it's sparkling clean, they dry it at 70 degrees Celsius for an epic 60 hours, then grind it up into a fine powder. Now here's where the magic really begins. They dive into what's called green synthesis of zinc oxide nanoparticles, or ZnO NPs. 2 grams of that algae powder gets mixed with distilled water, heated up to boiling, and filtered. The result? A liquid loaded with natural biomolecules. Next, this extract is combined with a zinc acetate solution, and sodium hydroxide is added drop by drop until the whole thing hits a pH of 12. They keep this mix at 65 degrees for up to 3 hours, and that's when a pale solid starts to form. These are the biosynthesized ZnO nanoparticles. After spinning it down in a centrifuge, rinsing and drying it overnight at 90 degrees, these nanoparticles are ready for the spotlight. But the story doesn't stop there. Now it's time to make the actual filtration membranes. Using a process called phase inversion, polyvinylidene fluoride, or PVDF, gets dissolved in a solvent called N-methyl-2-pyrrolidone and stirred until totally smooth. This solution is spread onto glass plates and left to rest for a bit. Then the plates are dunked in cool water, which causes the membrane to solidify right before your eyes. To crank things up a notch, the researchers whip up nanocomposite membranes. They mix in different amounts of those ZnO nanoparticles, 0.5%, 1%, 2%, and 3% by weight, straight into the PVDF solution before casting. This makes sure the nanoparticles are evenly locked into the membrane structure, ready to take on pollutants. Now, how do they know these membranes are actually working? Time for some high-tech analysis. They use scanning electron microscopy, SEM, to check out the surface structure, EDX for what elements are present, FTIR to see what chemical bonds are hanging around, XRD for the crystal makeup, and water contact angle measurements to see how much the membranes love, or hate, water. To put the membranes to the test, they're installed in a stainless steel cross-flow filtration cell with a 42 square centimeter active area. After an hour with distilled water to get things stable, the team measures permeate flux, basically how much water gets through, and, more importantly, how well the membranes remove hexavalent chromium, or CAR6, which is super toxic. They make chromium solutions by dissolving potassium dichromate into water, then diluting to different levels. Using a colorimetric method with diphenyl carbazide, they measure how much CAR6 is left at 540 nanometers on a UV-Vis spectrophotometer. From these readings, they figure out both the percentage of chromium removed and the adsorption capacity for each type of membrane. All this work leads to one big result. By mixing green nanotechnology with smart membrane engineering, these researchers created an eco-friendly, practical way to strip out heavy metals from water, turning a humble Egyptian algae into a force for environmental good. That's science in action. Thanks for watching For Science Salah Lotfy channel.
The journey from concept to reality began with the meticulous fabrication of our membranes. We chose polyvinylidene fluoride, or PVDF, for its robust chemical resistance, a perfect foundation. But the real innovation lies in what we added. Using a green synthesis method, we harnessed native marine algae to produce zinc oxide nanoparticles. This eco-friendly process avoids harsh chemicals and creates highly effective particles. After carefully designing and fabricating both the baseline PVDF and the advanced PVDF ZnO Nanocomposite membranes, I moved on to the performance evaluation, the moment where theory meets reality. This is the crucible for any new material. In the lab, we constructed a specialized cross-flow filtration system to mimic industrial conditions, challenging the membranes with water contaminated by hexavalent chromium. The key questions were simple: how much chromium could it remove, how fast could it work, and would it last? When I tested for CAR6 removal, a clear and exciting trend emerged. The data showed a direct correlation. As the percentage of zinc oxide nanoparticles embedded within the membrane increased, so did its performance. This wasn't a coincidence. The ZnO nanoparticles act as powerful, decentralized adsorption sites. Each particle is like a tiny magnet for chromium ions, pulling them out of the water and binding them to the membrane surface. We found the sweet spot. The optimized membrane, containing just 3 weight% of our algae-derived ZnO nanoparticles, achieved some truly outstanding results. First, a 91.69% removal efficiency for hexavalent chromium. This level of purification can take dangerously toxic water and render it safe for discharge, meeting stringent environmental regulations. Next, we measured an adsorption capacity of 10.92 micrograms per square centimeter. This figure tells us how much chromium the surface can hold, indicating a high capacity for pollutants before it needs cleaning. And perhaps most impressively, we saw a remarkable 50% increase in water permeability compared to the neat PVDF membrane. This means more water can be pushed through using less energy, a critical factor for making the technology economically viable on an industrial scale. So what was the secret behind this boost in permeability? The improvement is directly linked to a fundamental change in the membrane's surface properties. We measured this using the water contact angle. A high angle means a surface is hydrophobic, or water-repelling. The pure PVDF membrane had a contact angle of 75.4 degrees. But with the ZnO nanoparticles, that angle dropped dramatically to just 48.9 degrees, signifying a profound increase in hydrophilicity. In simple terms, the membrane became far more water-loving. This is crucial because it directly combats biofouling where contaminants clog the filter. By making our membrane hydrophilic, we create an anti-fouling effect, resisting blockage and allowing faster, cleaner, and more consistent filtration over time. To understand the chromium was captured, we delved into the kinetics. Our studies showed the removal followed a pseudo-second-order model. This technical term points to chemisorption. It means the chromium ions weren't just physically trapped, they were forming strong chemical bonds with the active sites on the zinc oxide nanoparticles. Furthermore, the isotherm analysis revealed that the Langmuir model was the best fit. This confirms the nanoparticles created a homogeneous surface where adsorption happened as a single uniform molecular layer. It's a testament to the perfect distribution of our ZnO nanoparticles, creating a highly efficient surface for detoxification. Of course, in the real world, a filter is only as good as its ability to be reused. Durability matters just as much as initial performance. We subjected the membrane to a rigorous test, 3 consecutive filtration and cleaning cycles using a simple acid wash to regenerate the surface. The results were incredibly promising. Over 3 consecutive filtration cycles, the removal efficiency dropped only slightly, from an initial 91.69% down to a still impressive 84.52% by the 3rd cycle. This minimal decline proves the membrane's structural integrity and the stability of the nanoparticles. It can be cleaned and reused effectively, which is the key to making it a truly cost-effective and practical solution for long-term industrial water treatment. But these results aren't just numbers on a page, they represent a lifeline for ecosystems under threat. Consider Egypt's vital industrial zones, particularly in sectors like leather tanning and textile dyeing, which are notorious for discharging chromium-laden wastewater, or agricultural irrigation systems. This technology offers a direct on-site solution. Implemented at the source, it could prevent toxic chromium from ever entering vital waterways like the Nile River, protect soil health, and ensure safer reuse of treated wastewater. From a broader environmental perspective, this work represents a paradigm shift towards circular, eco-friendly remediation. We are using a locally sourced, abundant natural resource, marine algae, to create a high-tech solution to a pressing industrial problem. This is green chemistry in action, turning native algae into a high-performance water purification tool. The research proves that these algae-mediated nanocomposite membranes aren't just a laboratory innovation. The path forward involves scaling up production, exploring modifications to target other heavy metals like lead or mercury, and conducting pilot studies in real industrial settings. The challenges are real, but the potential is immense. They're a blueprint for a sustainable, scalable, and economically viable solution for one of the most persistent environmental challenges of our time: offering new hope for water security. You're watching for Science Salah Lotfy channel, where science meets solutions for a better world. As we continue exploring the results of this groundbreaking study, let's dive deeper into the fine details that make these membranes exceptional. Energy dispersive X-ray analysis confirmed the successful integration of zinc oxide nanoparticles into the PVDF membrane matrix. The water contact angle dropped from 75.4 degrees in pure PVDF to just 48.9 degrees in the nanocomposite. This means water spreads more easily, enabling faster filtration. Removal efficiency peaked at pH 6. In the first 60 minutes, efficiency increased sharply, then plateaued at 120 minutes when equilibrium was reached. Different zinc oxide concentrations showed a clear pattern, from 9.43 micrograms per square centimeter at 0% ZnO to 10.92 at 3% ZnO. Over 3 regeneration cycles, efficiency dropped only 7.17%, from 91.69% to 84.52%. This means repeated use with minimal performance loss. Kinetic modeling revealed chemical adsorption dominates, with the pseudo-second-order model achieving an R-squared of 0.998, an almost perfect fit. The Langmuir model proved best with R-squared equals 0.984, showing uniform monolayer adsorption across the membrane surface. What makes this unique is the green synthesis approach. The zinc oxide nanoparticles are derived from Arthrospira platensis, marine algae from Egypt's Wadi El Natrun region. When benchmarked against alternatives, these membranes provide 91.7% removal efficiency, 50% higher water permeability, and high mechanical strength. In Egypt's industrial zones and agricultural areas, this technology could remove toxic chromium before it contaminates irrigation water. This research bridges the gap to real-world application, combining sustainable synthesis with advanced engineering for eco-conscious wastewater treatment. You've been watching for Science Salah Lotfy channel, where we bring you science that shapes our future, one drop of clean water at a time. Welcome back to For Science Salah Lotfy channel. In part 1, we explored how marine algae and green nanotechnology came together to produce advanced PVDF ZnO Nanocomposite membranes. Now we continue with the detailed results and their wider implications. One of the first critical findings was the effect of pH. The removal efficiency of chromium-6 varied significantly across different pH levels. A pH of 6 emerged as optimal, balancing both chemical stability and maximum removal efficiency. Next, the effect of contact time revealed a rapid uptake of CuRR-Cis within the first 60 minutes. This sharp initial rise indicates that at the start, the membrane surface had abundant available adsorption sites. After 1 hour, the process reached equilibrium, an important operational benchmark for scaling up into automated water treatment systems. Adsorption capacity was another key performance metric. The pure PVDF membrane achieved 9.43 micrograms per square centimeter, but incorporating ZnO nanoparticles steadily increased this value, reaching 10.92 micrograms per square centimeter at 3% ZnO content. This confirmed the active role of nanoparticles in capturing chromium ions. In industrial water treatment, reusability is essential. The membranes underwent 3 regeneration cycles. After each cycle, the removal efficiency decreased only slightly, from 91.69% in the first use to 84.52% after the third. That's a drop of just 7.17%, showing excellent durability and reduced need for frequent replacement. Such stability translates directly into lower operational costs and consistent performance over time, a crucial factor for municipal and industrial wastewater plants. To understand the underlying adsorption process, the researchers analyzed the data using 2 kinetic models, the pseudo-first-order and pseudo-second-order equations. The results? The pseudo-second-order model, with a correlation coefficient above 0.99, best described the data. This suggests that chemosorption, a chemical bond between the chromium ions and the membrane surface, is the dominant mechanism. Adsorption isotherm studies added another layer of insight. 3 models were tested: Langmuir, Freundlich, and Temkin. The Langmuir model fit the data best, with an R2 value of 0.984, indicating a uniform monolayer adsorption process. This is significant because it means the membrane surface behaves predictably, making system design and scale-up easier and more reliable. Compared to other studies, this membrane holds its own remarkably well. While some green ZnO nanoparticle systems achieved higher adsorption capacities in batch tests, this research integrates the nanoparticles directly into the membrane matrix. The benefits? No need for separate adsorbent powders, better stability and consistent performance in continuous flow systems, exactly what's needed for real-world applications. The environmental and economic implications for Egypt are profound. Industrial impact. These membranes could be deployed in factories that discharge heavy metal-laden wastewater, preventing contamination of local water supplies. Agricultural benefit. Cleaner irrigation water means healthier crops and reduced risk of heavy metal accumulation in the food chain. Economic advantage. Using a renewable marine algae source keeps production costs low while aligning with Egypt's sustainability goals. In conclusion, the PVDF ZnO Nanocomposite membrane, synthesized using eco-friendly marine algae, delivers a powerful combination of high removal efficiency, enhanced water permeability, and outstanding reusability. This innovation bridges the gap between laboratory research and large-scale environmental solutions, offering a cleaner, safer future for water treatment in Egypt and beyond. You've been watching For Science Salah Lotfy channel. Thank you for joining us on this scientific journey. Welcome to For Science Salah Lotfy channel, where we transform advanced research into engaging stories. Today we explore a cutting-edge study that bridges marine biology, nanotechnology, and environmental engineering. The research is titled Marine Algae-Mediated PVDF ZnO Nanocomposite Ultrafiltration Membranes, Superior Performance in KRS6, Removal from Aqueous Solutions. It was published in Environmental Science and Pollution Research, received on March 27, 2025, and accepted on June 27, 2025. The team behind this remarkable work includes Dr. Mohamed Khedawy, Marine Pollution Research Lab, Marine Environment Division, National Institute of Oceanography and Fisheries, Cairo, Egypt; Professor Dr. Abir Monir, Dr. Azza Shaker, Professor Dr. Mohammed Shafiq Ramadan from Alexandria University, and Associate Professor Dr. M.N.A. Fadl. To create these advanced membranes, the researchers used a combination of commercially available materials and naturally derived compounds. Key chemicals included zinc acetate dihydrate, potassium dichromate, and sodium hydroxide. The base polymer, PVDF, came from Alpha Isar in the USA, but the real innovation began with the collection of Arthrospira platensis, a type of marine algae. Samples were taken from El Khadra Lake in Wadi El Natroun, Egypt. They were carefully washed, dried at 70 degrees Celsius for 60 hours, ground into fine powder, and sieved to ensure consistency. From this algae powder, the team synthesized zinc oxide nanoparticles using a green, eco-friendly method. The dried algae extract was mixed with zinc acetate and sodium hydroxide was added drop by drop until the solution reached a pH of 12. The membranes were fabricated using the phase inversion technique. First, a casting solution was prepared by dissolving PVDF in the NMP solvent. This solution was spread onto a glass plate, allowed to partially evaporate, and then submerged in a cold water bath to solidify. To create the nanocomposite version, zinc oxide nanoparticles were added to the PVDF solution in varying amounts, 0.5%, 1%, 2%, and 3% by weight. The membranes underwent rigorous characterization. Scanning electron microscopy revealed surface morphology and pore structures. Energy dispersive X-ray confirmed the presence of zinc oxide. FTIR identified functional groups. X-ray diffraction provided crystal structure data. One critical property studied was hydrophilicity, measured by the water contact angle. A smaller angle indicates a more water-attracting surface. The incorporation of ZnO nanoparticles reduced the WCA dramatically, meaning water could spread and pass through the membrane more easily. Performance testing involved a stainless steel cross-flow filtration system. The membranes were first conditioned with distilled water, then challenged with chromium-contaminated solutions. Permeate flux and the concentration of remaining chromium were measured precisely. The best-performing membrane containing 3% ZnO nanoparticles showed a 50% higher water flux and significantly greater chromium removal.
In conclusion to this episode, I would like to take a moment to express my deepest gratitude. I am Professor Dr. Salah Lotfy, professor at the Egyptian Atomic Energy Authority. And on behalf of my channel, For Science Salah Lotfy channel, I extend my heartfelt thanks to the esteemed researchers for their remarkable efforts in this outstanding scientific work. First, my thanks go to Dr. Mohamed Khedawy from the Marine Pollution Research Lab, Marine Environment Division, National Institute of Oceanography and Fisheries, NIOF, Cairo, Egypt. Also to Professor Dr. Abir Munir, also from the Marine Pollution Research Lab, Marine Environment Division, NIOF, Cairo, Egypt. My appreciation extends to Dr. Azza Shaker from the Chemistry Department, Faculty of Science, Alexandria University, Alexandria, Egypt. I would also like to thank Professor Dr. Mohamed Shafiq Ramadan from the Chemistry Department, Faculty of Science, Alexandria University, Alexandria, Egypt. And finally, my sincere gratitude to Associate Professor Dr. Emin Fadel from the Materials Science Department, Institute of Graduate Studies and Research, Alexandria University, Alexandria, Egypt. Your combined expertise and dedication have resulted in a study that not only advances the frontiers of science, but also holds real promise for environmental and industrial applications, especially in enhancing water quality and protecting ecosystems. To my valued audience, I thank you for following this journey with us. I invite you to share your thoughts and questions about this research in the comment section below the video on the channel. Your engagement helps build a community where science is discussed, appreciated, and applied for the benefit of all. This is Professor Dr. Salah Lotfy, signing off from For Science Salah Lotfy channel. Until our next episode, let us continue to explore, discover, and inspire through science.